Hey, Science, and welcome to topic 1.2 of the Space Exploration Unit Discovery through Technology. Today, I want to discuss a little bit about the history of technologies that have been used to sort of help scientists make certain major discoveries in astronomy. We're going to discuss a few in particular, especially the telescope today, that I will be discussing in greater detail later in the unit because there are many different types of telescopes that are now in operation that are being used for all sorts of different reasons, different sizes, different locations, different types of light energy that they can actually detect. But for today, I just want to kind of go through a brief history of the uses of technologies throughout, I guess, scientific history that led to some of the discoveries that I discussed with you last day in our last topic 1.1, where I discussed some of the groundbreaking science that were done by scientists like Copernicus, Galileo, Kepler, Brahe. So I'll be discussing that today. There's a few, I guess, ancient technologies that have been out there for a very long time that have been helping people chart where position of objects are in the sky, whether it's the sun or the moon or the stars. Um, the One of the oldest ones is the sundial. The sundial's been around for 7,000 years, and it's essentially one of the oldest versions of a clock. It would create a cast of shadow, and that shadow on the sundial would basically allow people to tell time based on where the sun was in the sky. So again, that indicated that the ancient peoples who designed these sundials understood that the sun was moving through the sky, and you could indicate time of day based on where the sun was at any given part of the morning or afternoon. Then you get what's called a mercat, which is basically was invented by the Egyptians, and it was designed to chart astronomical positions, and it was able to predict the movement of stars in the sky. So if you would look up into the star, see a star in the sky, you could sort of predict where that star might move later in the evening using this technology. So again, they were able to determine and kind of made observations that in the night, your stars are moving. The stars do move in the night sky over long enough periods of time. You may not be able to see it with the naked eye, but you might see the Big Dipper is in this place of the sky at 10 o'clock at night, and then the Big Dipper might be over here by 12 o'clock in the morning. So these were observations that these early scientists, were able to make, and then they made this technology, this mercat, that would allow them to chart the position of the stars and where they were going in the sky. Then you have what's called a quadrant. The quadrant's been around for a long time. It was invented by the Egyptians, and it was able to measure the height of the star on the horizon. So if you were to see a star on the horizon, you could use a quadrant to basically calculate the relative angle, the relative height of the star in the sky. And we'll be discussing this a little bit later in the unit. We're going to come back to this later on when it comes to what's known as the altitude and azimuth of a star position when we get to that later on. But quadrants have been used for centuries by sailors to chart positions of the stars in the sky and what their relative positions are to get kind of a fixed reading of where they are when they're out in the middle of the ocean and have no land masses to get a bearing reading off of. Then you also have astrolabes, which were invented by the Arabians during the first 1,000 years after Christ, around probably the 600 to 700 AD range, somewhere in there. They made accurate star charts, and again, these were used by ships, navigators at night, so ships could sail at night based on the position of the stars in the sky. So this technology, this instrument, was used to again allow for navigation over great distances, and this is one of the big things that the Arabians did at that part when they were expanding their empire around the Mediterranean. They were able to move great distances, and a lot of times they could move during the night, no issues, because they could basically they had basically star charts that they had created using these devices. And the final one that was used again for navigation was one called a cross staff. This was designed to measure the angle between the moon and any given star. So knowing where the moon was in relation to a star, you could measure it using this device known as a cross staff. So most of these devices that were in there were used to either tell time or to tell relative positions, but you couldn't really see the stars or the things in the sky very well. Like you were always making these observations with the naked eye. That changed in the early 1600s with the invention of the telescope. And that was in 1608, and it was by a gentleman by the name of Hans Lippershey, who was a German. He was a glassmaker. He made glasses, and he designed this. And basically, a lot of people think Galileo invented it because Galileo was one of the first scientists to actually make great use of the telescope. He was basically making most of his observations, about Jupiter and Saturn, and he even discovered Neptune. He made observations of Neptune. He didn't realize it was a planet, but he didn't get credit for discovering the planet, but he had made observations of Neptune. So he even saw that planet several hundred years before it was actually officially discovered in the 1800s. But there was a telescope that allowed scientists and astronomers to be able to see these objects in the night sky in a magnified view, which began to open their eyes as to what was going on. And like I said, we'll be discussing more about telescopes later in the unit. There's a whole section about different types of telescopes. But for now, just be aware that it obviously opened the door to a lot of the discoveries that were made when around the time of Galileo, Copernicus, Kepler, Brahe, all those discoveries about the geocentric universe. The proof of them was found by using telescopes. So a very important tool, and it's still a very important tool even now. It's just the telescopes have gotten way bigger, way stronger, way better at actually seeing further and further into the universe. Now, again, the universe is big. Probably one of the stupidest things I've ever said, but the universe is really big. And so how do you measure it? How do we use measurement to measure the universe? I mean, we could use kilometers, but kilometers work well when we're dealing with, I'm going to travel from Edmonton to Calgary, which is 300 kilometers. But what happens when your nearest star is Proxima Centauri, which is like roughly 40 trillion kilometers away? You get really big numbers and they can become really bulky. And we sort of discussed this in the electricity unit when there were different types of units for energy. We discussed how you could use joules to measure small amounts of energy, and you could use kilowatt hours to describe large amounts of energy. Well, in distances, if you have a smaller distance, you can certainly use kilometers. But when you get up into the distances that are in space, kilometers really don't mean much. There's really no sense of how big things are. You're getting just numbers that are really, really tough to work with. So what do we do? Well, we created what astronomers did is they created two units of measurement. If you're measuring things in the solar system, in our relative neck of the woods here, around the sun and heading out toward, let's say, Pluto or whatever, we're going to use a unit known as an astronomical unit. An astronomical unit is roughly 150 million kilometers, and it is the distance between the sun and the Earth. So that is that one. So the Earth right now is 1 AU from the sun. So that would give people an understanding that, okay, if I know my distance from the sun to the Earth is 1 AU, then if I know that Proxima Centauri, which again is this the closest star to the sun, I said it was 40 trillion kilometers away. Well, if I put that into astronomical units, it would be 268,700 astronomical units. So that tells us that that star is about 250,000 times further away from the sun than we are. That might give us a better understanding of where that star is in relation to the sun, right? So that would be, but that's still a big number. That's still a big number. So once we get outside of our solar system, we use even a larger number. We use a number known as a light year. A light year is sort of the standard measurement unit in astronomy, and it's essentially equal to the distance that light can travel in 1 year. Now that works out to roughly, 1 light year works out to roughly 9.5 trillion kilometers in a year. Or sorry, it'd be 9.5 trillion kilometers that the light could move in 1 year, but that's the distance in kilometers. And if you're dealing with astronomical units, it's roughly 66,000 astronomical units. So you can see that by using light years, We're essentially taking 9.5 trillion kilometers and shrinking it down to 1 unit. We're taking 66,000 astronomical units and we're shrinking it down to 1 unit. So, generally speaking, once we leave the solar system, we're talking in light years. And again, the closest star to us is this Proxima Centauri, and it is 4.2 light years away. Remember, it was originally, I mentioned, it was 40 trillion kilometers away, or 268,700 astronomical units away, or in a much more manageable measurement, a light year is only 4.2 light years away. So that's sort of why we need to create, scientists have to create measurements that were more appropriate for the vast distances that are found in space, because that's only the closest star to us. Imagine when you're dealing with other stars that are further away. And let me just finish up today by discussing that. The deeper into the universe you go, the further back in time you go. You have to understand that if we're looking at the light that has traveled let's say it's 3 million light years away. That light took 3 million years from that star or that galaxy to reach Earth. So we're literally, when we look at an object that's that far away from us, we're looking back 3 million years in the past. If we see an exploding star that's 20 million light years away from us, that star is not blowing up right now. That star blew up 20 million years ago. So the further back in time, or the further away from the Earth we go when we're looking at the depths of space with a telescope, the further away we can see, the further back in time we can. And right now, the furthest away we've been able to see using the Hubble Space Telescope is a galaxy known as GNZ11. It's a constellation in the Big Dipper, and it has been discovered to be a distance from Earth of 13.2 billion light years away. So that galaxy right now, the light we're seeing from that galaxy is actually 13.2 billion years old. We're looking at that galaxy the way it would have looked like back then, not like as it appears now. Now, that's crazy, because if you think about the age of the universe, the further into the universe we can see, the closer back in time we get to the formation of the universe, a little thing you might know as the Big Bang. The Big Bang is supposedly would have occurred, scientists believe it was around 13.6 to 13.8 billion years ago is when the universe formed, when all the universe collapsed in on itself and then exploded. So if we can find objects or galaxies that are that far away from us, we're looking closer back in time toward the formation of the universe. So that's why scientists are always looking for objects that are further away from the Earth, because we can see what the universe looked like closer to the Big Bang. It's like having a time machine. Having a telescope is like having a time machine, because the further away from the Earth we can see, the further back in time we can go, and that we can actually see things that occurred in the past, not things that are occurring now. So that's kind of a cool fact, that we're dealing with such large distances that we can actually time travel. In a way, we're time traveling by looking through telescopes. So it's kind of cool that way. An interesting fact. That's our conversation for today. Our introduction to technologies that have revolutionized astronomy and some of the units that we use to measure distances in astronomy. For homework, I'd like you to complete questions 1, 3, 4, and 7 and 8 on page 383 of your textbook, and that will be due for next day. Please join me next time when I discuss our next topic in the fascinating area of space exploration. Won't you join me, folks? Take care.